sir, from VIT Chennai. I welcome you, sir. At this juncture, I would like to take the opportunity to share few words on our college and Department of Electronics and Communication Engineering, Pallavi Engineering College, Hyderabad. Our Pallavi Engineering College is at Nahul, Hyderabad. It is a green campus college, well-renowned institution which offers 5 engineering courses, includes Electronics and Communication Engineering, CSE, Civil, Mechanical, and Triple E, and 3 more diploma courses in Civil, Mechanical, and Triple E. And this year, we also added 2 more new courses in CRC, Data Science and Cyber Security, on par with industry standards. Now, we will see the short review of our department, Electronics and Communication Engineering. The Department of ECE is committed to providing quality professional education to aspiring engineers. The mission of the department is to facilitate
to share few words on our college and
engineers
Department
to
of
acquire
Electronics and
technical
Communication Engineering,
exposure in
Pallavi
the
Engineering
areas of
College,
electronics and
Hyderabad. Our
communication
Pallavi Engineering
engineering
College is at
to
Nahul,
nurture
Hyderabad.
career improvement and
It is a green
development,
campus
human
college,
and social
well-renowned
intellectual
institution
qualities necessary for
which
the
offers 5
successful
engineering
practice of the
courses,
profession.
includes
The
Electronics and
department has an
Communication
annual
Engineering,
intake of
CSE,
120 students. The
Civil,
department has well
Mechanical,
experienced and
and
dedicated
Triple E,
faculty and 3 more diploma courses in civil,
and aims to
mechanical,
impart sound
and
knowledge and
Triple E.
awareness in the latest
And this
trends in
year,
the field
we
of
also added
electronics
2 more
and
new courses in CRC,
communication
Data
engineering.
Science and Cyber Security.
We do more activities on students' guided
On par
career
with
guidance
industry
and various
standards.
promotional
Now, we
schemes.
will see the
Industry
short review
related
of our
updates,
department, Electronics and Communication
placement
Engineering.
training and activities,
The
and
Department
from
of
VIT
ECE
Chennai
is committed to
trainings. I
providing
welcome you,
quality
sir. Good infrastructure,
professional
at
education
this
facilities to
juncture,
aspiring engineers. The
I
mission
would
of the
like to take the
department is to
opportunity
facilitate
to
quality
share few
learning
words on our
process.
college and
Engineers
Department
to
of
acquire
Electronics and
technical
Communication
exposure
Engineering,
in
Pallavi
the
Engineering
areas of
College,
electronics and
Hyderabad. Our
communication
Pallavi
engineering
Engineering
college
College
is
is
at
at
Nahul,
Nahul,
Hyderabad.
Hyderabad.
Career
Thank you, sir.
improvement and
It
experienced and dedicated faculty
Now I
and 3 more diploma courses
like
in
to
civil,
aims to
mechanical,
impart some
and
knowledge and
Shravanti
awareness
ma'am to
in the
share
latest
and this
few
year
words
we
about
also added
electronics
2
and
more new
communication
courses in CRC,
Communication
Data
Engineering.
Science
Today's
and
presenter, Dr.
We
K.
do
Mohan
more
Prasad,
activities
sir.
on students' guided
On par with
career
hello,
guidance
ma'am,
and
various
various.
promotional
Now we will
schemes.
see the
Industry
short review
related
of our
updates,
department, Electronics and Communication
placement
Engineering.
training and
Shravanti ma'am,
activities,
the
and
Department
from
of
VIT
ECE
Chennai
is committed to
trainings. I
providing
welcome you,
quality
sir. Good
Hello, ma'am.
infrastructure,
Can you
at
hear
this
me?
facilities to
juncture,
aspiring
yes,
engineers.
ma'am, yes,
The
ma'am. I
mission
would
of the
like to take the
department is to
proceed, ma'am.
Ma'am, can you hear me now? Epsiba, ma'am.
Yes, ma'am.
Uh, Thank you very much, ma'am. It is an honor for me to.
Yes, ma'am. Yes, ma'am.
Thank you very much, ma'am. It is an honor for me to introduce our guest, K. Mohan Prasad, who was born in India in 1981. He received his PhD degree in the field of speech signal processing from VIT University, India, and postdoctoral research fellowship from University Tunku Abdul Rahman, Malaysia. He did his Master of Engineering in Applied Electronics from Anna University, India, and the Bachelor of Engineering degree in Electronics and Communication Engineering from the University of Madras, India. Currently, he is working as an associate professor in the School of Electronics Engineering, VIT University, Chennai, India. He is the author of more than 3 Scoopus Index book with Scoopus Index book chapters edited, Scoopus Index book with professors in NTU Singapore, more than 25 international journals and international conference publications. He is currently doing the industry project with Samsung R&D Bangalore. He published a patent with a little smart mirror. His research interests include signal processing, speech processing, wavelet transform, machine learning, and deep learning. Good morning, sir. We request your heartily welcome for this session, sir. I request you to start this session, sir.
Yeah, thank you, ma'am.
Thank you, sir.
I thank everyone to give this opportunity for me to have a sharing,
సార్
mutual sharing.
వస్తుంది సార్ అది యూట్యూబ్ అని పెట్టాలి సార్ అది పెట్టలేదు నేను వస్తుంది ఓకే థ్యాంక్ ఓకే థ్యాంక్ యూ సార్
Hello, are you hear me?
ఎస్ సార్ ఎస్ సార్
Yeah, I thank everyone to give the opportunity here. for giving a wonderful lecture on introduction to wavelet
Wavelet
transform and its
transform, machine
application.
learning.
Why this particular topic now is taken? You know, now in worldwide, everywhere, data, a huge set of data are available, and data processings are very important, and it is an important requirement for doing a machine learning and deep learning algorithms, right? So everywhere, all the data are processed by machine learning and deep learning. Using with the help of that, we can able to do so many interesting things. But the problem here is the data as it is in the form of raw data cannot be processed in machine learning or deep learning or a very recent technology. It is not possible. We need to do some data cleaning with help of the pre-processing techniques. So I feel this even now many research papers they depends on this wavelet transform for pre-processing of data, right? So with the help of the pre-processing of data, then they go for a machine learning algorithms or a deep learning algorithm, it works. Otherwise, it's difficult and the accuracy and the efficiency are very less without data pre-processing. So that's why I took this topic as interest for today's lecture, the introduction to wavelet transform and its application. So first, we will go for transform generally. Why we are going for transform? A transform convert a signal from one domain to another domain, you know. So we can convert a time domain signal into a frequency domain, which we call it as a Fourier transform. And then a time domain to S domain, so Laplace transform. Time domain to Z domain is a transform. And so many transforms are available. So why we need this transform? Transforms are useful for fast computations of your mathematical operations. For example, if you want to do a differentiation, integration, convolution, correlation, or any other mathematical operation, it will be very faster in case of transform compared in a time domain. For example, if you take a convolution, if you want to perform a convolution in a time domain, you need to fold a signal, then you need to shift the signal, then you have to multiply with the original signal, then you have to submit. So you have to do 5 steps for doing the convolution operation. Whereas in Z domain, we simply convert to Z domain, then you simply do the multiplication of those two data, and then we can perform convolution operation in a simpler way. So that's what the need of transform is important for fast computation. As well as it also reduces the data storage. So you want to reduce the unwanted elements present in the data can be reduced with the help of these transforms. So the compression of the data is possible. And also it is used for pre-processing of data. As I told previously, like data cleaning and data pre-processing is very important. So for those things, even a machine learning separate, there is no separate pre-processing techniques available, or deep learning, there is no such a pre-processing technique available. So it depends on all transforms. So either you can use your wavelet, or you can use your decomposition, poly eigenvalue decomposition, any kind of decomposition they are using. Yeah, the next one. So generally a transform means, right? So a positive real number, if you take f of t is a function, it will be an integral transformation of a to b k of s comma t into f of t into dt. But ks of f comma t, we call it as the kernel of the transformation. This is called the kernel of the transformation. On this kernel, we are deciding whether it is a Laplace transform, it is a Fourier, or it is a wavelet. It depends on the kernel of the transformation. So generally, we see, if you see the k of s of t is equal to e power minus st. If you substitute the limit of a varies from 0 to infinity, then that previous equation becomes a Laplace transform. Right? So and generally, if the same thing is, if you substitute k of a positive real number, if you take f of t is a function from minus infinity to plus infinity, then it is a Fourier transform. Similarly, you have a k of st as cos st and sin st, then it is Fourier cosine and Fourier sine transform. When it is t power s power minus 1, we call it as a Mellin transformation. So everything is based on the, depends on the, what we call it as the kernel of the transformation. So here, Fourier analysis on the kernel of the transformation. Wavelet, before going to wavelet, what is the disadvantage? If you see the limitations, you have t is the previous analysis minus st. If you substitute, we start with the Fourier varies from 0 to infinity. Then that previous equation becomes I think I will give a small example. So maybe the same thing, understand the concept of Fourier as even like. You know, all Tirupati, daily there will be a big hundis will be there, and then contribution by the devotees to the hundis will be happening. More huge money will be there. So how they are doing the denominations, how they are separating the denominations with the help of the concept of Fourier series, Fourier transform, and Wavelet transform. There is a separate statistical department will be there. So for example, if you want to know, like in particular day, what are all the denominations available? For example, a 10 rupees note, a 500 rupees note, or a 100 rupees note, denominations are available or not. You can do Fourier series. So you have a Fourier series. If you do the Fourier series, it will give you what are all the denominations. Denominations, like what we actually do is the Fourier series will give you what are all the frequency in a particular signal. So it is given by Fourier series. Then what the Fourier transform will do? In that particular example, if you want to know how many 100 rupees notes are available, how many 500 rupees notes are available, so that can be given by the information of Fourier transform. If you see what is the frequency involved in it, the 5 kilohertz frequency is involved, and what range from where to where the 5 frequency 5 kilohertz range of frequencies available. That information will be given by Fourier transform. And then what is a wavelet transform? Now, our field of interest, wavelet transform. In the same example, if you do all the denomination 100, 200, you want to know the statistics of 10 a.m. to 11 a.m., how many 500 rupees notes are available. So you will get the time information with corresponding frequency information. Right, that's 500 rupees notes are available. How many 500 rupees notes are available in at the time of 10 a.m. to 11 a.m. So this will be given by a Wavelet transform. So like that in the actual scenario, so you have frequency from 5 kilohertz to 10 kilohertz in what particular time, and 20 kilohertz to 30 kilohertz at what particular time. So that will be given with the help of a Wavelet transform. So this is what actually why these transforms we are using in our day-to-day life. So as you know, I given an example of Fourier series. If you see, you have a signal of some frequencies, a signal of another frequency. Addition of these two frequencies, you will get a waveform like this in a time domain. So we are not able to get any information in a time domain frequency signal or time domain signal of different frequency. It will be multiple of frequency, but we cannot able to identify it. It's difficult to do it. So this is how the frequency look like when you add more frequencies. Then we'll use the signal Fourier analysis to get this kind of spectrum. So the spectrum says what frequencies are what are the frequencies available in a particular signal. So you have in this signal two different frequencies, so you'll be getting two spikes in it. So each spikes represents some frequencies in it. So this is how why we go for Fourier analysis. So what is the serious draw in a Fourier analysis? Why we are going for the next waveform or wavelet transform? The serious drawback in transforming a frequency domain thing is time domain information will be lost in many cases. In many applications, it will be get lost. So looking at the Fourier transform of a signal, it is impossible to tell when a particular event took place, right? For example, if you want to know that frequency happening at what time, there is a change in the frequency. For example, you have a continuous waveform at 5 kilohertz. Now it is going to change to 10 kilohertz. What time it happens, we don't know about the time information. So the two main drawbacks we have is the loss of information as well as you have a time information is missing in a Fourier analysis. So this is what like I told you, so the same thing, the signal with the multiple frequencies. So when you do the Fourier transform, you get a different frequencies can be possible to get the information. So now what they did after that Fourier analysis, they went. The professors Dennis Geber in 1946 given a short time Fourier transform. So yeah, this is using a windowing, a particular windowing, so you can able to get a time information, but time information of the particular signal along with the frequency. But we have a short drawbacks here also. So the same as usual Fourier transform, but data is modified by multiplying with a window function. So we can say this is our window function. When you multiply with the time series or time signal, then only that window, based on that window function, the signal will be available. So after your multiplication in case of short time Fourier transform. So one of the drawbacks, frequency and time resolutions are fixed for a window, right? Whatever window you're using, for that particular window, the time resolution, frequency resolutions are fixed. So wider the window width, lesser the time resolution, more the frequency resolution. So it's reverse vice versa, right? We can say in the other way. The frequency resolution increases, time resolution decreases. That is the uncertainty principle in a short time Fourier transform. So what is the desired thing? We need a good time resolution at high frequencies and good frequency resolution at low frequency. So how to achieve this particular desired thing? It is possible with the help of Wavelet transform. So it's further with the short time Fourier transform. It analyzes the signal by multiplying by a window function and performing an orthogonal expansion analogous to another linear integral transformation. So a wavelet, we call it as a series represents of square interval function with respect to complete orthonormal set of basis function, which we call it as wavelet. The meaning of wavelet is a small wave. A wavelet is a waveform effectively limited duration, and as average value, if you take, it will give a 0. So you have different types of wavelet transforms. You have continuous wavelet, discrete wavelet, fast wavelet transform, wavelet packets, then complex wavelet transform. So here, so what are the principles of wavelet transform? So the wavelet transform analysis is breaking of a signal into a shifted, scaled version of the original signal, which we call it as a mother wavelet. So representing the same signal, but all are corresponding to different frequency bands. So only providing what frequency band exists at what time interval. So this is what our ultimate principle. The main thing is we are splitting a signal with a different frequency bands, but these frequency bands exist at what time interval. So it is possible. How it is possible? By using a wavelet, a mother wavelet. A mother wavelet is shifted and the scaled version of the original mother wavelet is shifted and scaled version, and that can be used to break up your original signals. So here, what are the properties, other properties? We have a possibility of time shifting, flexibility, and short time localized of wave with zero integral value. So this is the other properties. So when you talk about the continuous wavelet transform, it is defined as sum of overall time of a signal. This is a signal f of t. When it is multiplied by scaled and shifted version. So it's a scaled version and shifted version of your wavelet function. Then you get the continuous wavelet transform. So this is what multiplying each coefficient by the appropriately scaled and shifted version. So this is your wavelet, your mother wavelet. It is now scaled, and it is scaled actually, it is scaled and it is get shifted from one place to other place. When we multiply this kind of thing, so you can see here, so this values get multiplied with the time domain signal. This is your time domain signal. So that wavelet will not be fixed like STFT in a particular position. It will be scaled every time and then it will be shifted based on the input requirement. Right? We have to scale and shift based on the input requirement. So each and every input has different structure, shape, and property. So we can scale our information, a wavelet, based on the input requirement. That is a big advantage of using this wavelet transform. So what exactly we'll do? What operation we'll do? So you see here this particular thing diagram. So you have the time domain signal in the purple color, and then initially the wavelet what we use in the red color. Now it is translated, that is your shifted, and is also scaled. So because at this particular juncture, it need the scaling or not, that scaled version should be small, and here the scaling should be large. So based on the input requirement, it is scaled and shifted, right? So once you do this and multiply with the time series, then this sum of this product will give you the wavelet coefficient in terms of tau and scale. That is shifted and scaled version. So what actually scaling is? So you have a signal sine t, right? This is your signal. Then when a equal to, it's actually a into t. When a equal to 1. So if you do that value a equals to 1 by 2 here, then what happens? It's then compressed. The value will be get compressed here. That is the actual meaning of what is scaling is. Further, if you use the value of a is 1 by 4, then it will be, so it is actually sine 1 by 8, right? So then further it is scaled down, right? So this is the compression. We are doing actually the compression of the original signal. So even what is scaling, it is in case of a wavelet, this is for the particular signal, any sine signal, it is a wavelet. So this is a mother wavelet. We have a different mother wavelets we have, right? So these mother wavelets are designed by a different scientists. Even we can design our own mother wavelet based on our decision or based on our input. We can design our own mother wavelet. So the psi of t can be defined by the inventor, by the experimented person, because he knows what kind of information is required or what kind of information is needed. So for that, a scaled version is required. So here, this particular wavelet is scaled down to 2t, a is 1 by 2, and 4t, it is 1 by 4. So based on our input, we can scale down the process. So this is what actually a signal, and then if you use a low scale, what happens if you use a high scale? So that is scaling is, if you improve the scaling here, low scale, the compressed wavelet you will get, and rapidly changing the get, and you get high frequency omega. Whereas if you use a high scale, then stretched wavelet, you will get a stretched wavelet, slowly changing coarse features, and low frequency information required. Because every time which is required for the particular information or data, you need always a low frequency information is required. Because all the high frequency information consists of a detailed component. What is the meaning of detailed component? It has a more detail in case of suppose one song you are taking or any music with the speech you are doing, a particular song, the song who's playing that particular part will be consist of low frequency, and the drum beats other musical notes will be considered to be the high beats or that are high frequency information. So always we require low frequency components, so go for a high scaling that is required. And what is shifting? So these, if you understand these two concepts, scaling and shifting, you can design your own wavelet based on your own application. Your application may be anything. It may be a radar signal, it may be a ECG, electrocardiogram, or it may be your EEG, EMG, or some other signal like even leak signal in a pipeline. Even the mechanical people don't know that. Like, so you want to find the leak detection. It's one application. Leak detection in a pipe. You want to find where is the leak available. So then also, the leak signal will be mostly distorted one. So in that way, you want to design our own wavelet, which I did in my postdoctorate, right? So we did a project in Malaysia. The project is a government project. Like not like India, everywhere, even a big apartment from lower people to higher people, the government only will supply water in Malaysia. So we cannot drill a bore or take a water from the ground without any permission from the government. So what the people, Malaysian government is distributing a water throughout Malaysia. So they found there is more wastage of water due to leak. This is what the project given to the particular university by the government of Malaysia, and I was one of the signal processing engineer. So they took me for the postdoctorate with a thing, and we'll go there. And what is my role exactly? I want to find the leak. They will take the data. They will design a sensor. They use an acoustic optic fiber sensor. They design their own sensor. With the help of the sensor, they found out the leak present in it, and the leak cannot be directly found. Only the data can be taken from the sensor. The data will be given to me. The data is a very raw data, huge noise in the pipeline. The pipeline water flowing noise will be there. Atmospheric noise will be there. So by seeing the data, it's a very random in nature. I cannot be able to predict what kind of noise is added. So step by step, what I decided to design our own wavelet based on the particular raw data. So what we did, so we designed a wavelet called Moore wavelet. So that is one of the scientists. We given a mathematic equation. We used that equation, but he didn't design wavelet. He invented that equation. Using that equation, we found that equation will be helpful to us to design a wavelet, and we design our own wavelet, and it's worked very well actually. So the project is 75% completed totally. My part 100% I completed and come out. So further they are doing for IoT thing. So how the leak detected now. Where is the leak detection? I will say that they have to transfer that information to the worker who is working there. So that kind of information is going on. So why I am saying this particular example to you is, so how important it is to design your own wavelet. If you understand the concept of shifting and scaling property, you can design any wavelet on your own, right? So here the shifting comes, the wavelet function. In this wavelet function gets shifted. So this is at origin it started, and it is shifted by k times, right? The k towards the right, and that is phi of p minus k. This is a shifted version of the wavelet. So now generally, if you want to write a single dimension wavelet function, phi a comma b of x, which is 1 by root a, it's a is a scaling coefficient, right? It's a scaling coefficient, and x minus b by a, where b is nothing but the shifting coefficient, right? Using this, we can design our own wavelet function. Now, if you want to write the same equation in a 2-dimension for an image, then it is phi of a. Then that is your scaling will be only one, so a, and a shifting will be happens with respect to x and y coordinate, bx and by. So that's what you're getting, x minus bx by a, y minus by by a, right? So these will be generally the plots of the continuous wavelet. Continuous wavelet will get, so the small coefficient will be a darkly shaded region, and a lightly shaded region will be a large coefficient. So based on that, you have to identify what kind of informations of time is available, right? So here the frequency will be at this particular time, and the frequency will be high in this, that is the frequency present at this particular time will be a low frequency, and this particular frequency will be a high frequency. This kind of information is the plot. This is just an example of some other data. So wavelet families comes like it is different wavelets, Haar wavelet, debauchish wavelet, and then so many wavelets are available. So how the Haar designed a scaling function? They use a square form of scaling function and wavelet function as a rectangular on-off square pulse, and debauchish uses this particular form. So mostly these two wavelets will be well suited for all kind of application. Sometimes, as I told you, if the data is rough and random, it is very difficult to use even these Haar functions. So after that, in debauches, we have a different families, DB2, DB3, DB4. It's the shifted version and scaled versions are sometimes modified, right? So the other classes of wavelets, we have a far, we saw that, perfect, Mayer, Gaussian, Mexican hat, and Motlet. These are some of the examples of wavelets what actually designed. So these say some uncertainty in case of your continuous. After we decompose a signal and represent in time domain, we can see which frequency exists at what time. That is okay. The uncertainty principle, Eisenberg says that we are not able to predict the momentum and the location of a particular to 100% of certainty. That is not possible in case of continuous. Always continuous, there will be a disadvantage compared to a discrete. So what is final conclusions? We are not able to know exactly what frequency exists at a single time instance. We can only predict. That is the problem in case of continuous wavelet. So the frequencies are accurately over a longer period of time or vice versa. So these are the 5 easy steps. I recalling the steps what you have to do. Take the wavelet and compare it to a section at the start of the original signal. So this is the original signal. Take the wavelet, right, and then calculate the correlation coefficient. Then shift the wavelet to the right and repeat 1 and 2, calculate the correlation coefficient. So you do a similar process for the entire signal. And fetch the wavelet and repeat step 1 to step 3 and repeat step 1 to step 4 for all scales. These are the easiest step for doing continuous wavelet transform. So why I am more particular about this one is everyone they are doing a wavelet, right? So simply what they will do, they go to the MATLAB and they use DWT function, right? So DWT of something and then they get the answer. They say, yeah, I did the wavelet transform. It is not actually a wavelet transform. You must understand about the importance of the data, how your data is. Your data is like a baby, like you have to train the data and shape the data in one particular form for the certain applications. So for that, you need to some disturbance is there. Someone will mute the thing. Yeah. So thank you. So this is how. Next we go for the discrete wavelet transform. Actually I'm running out of time. I can stop. So yeah, no. So discrete wavelet transform. Why discrete wavelet transforms is needed? As I told, we have certain limitations in the continuous, so we go for discrete wavelet transform. The other hand provides us sufficient information for both for analysis and synthesis of an original signal with significant reduction in the computation time. This is another main advantage of using a discrete wavelet transform. The computation time saves in terms of your discrete wavelet transform. The DWT is considerably easier to implement when compared to CWT. That's what we go for DWT. So this is a point, same thing, so I don't want to do this. So generally we directly go for direct wavelet, discrete wavelet transforms. Here, what is the decomposition? So you have two things, analysis and synthesis. So analysis is the part like what we decompose and then once again goes to the reverse back. This one we call it as synthesis. Right? Any signal you have, the signal can be passed into two stages. One is a low pass filter, another one is a high pass filter. So low pass filter will give you approximation coefficient and high pass filter will give you a detailed coefficient. So this approximation coefficient consists of maximum information content. So your information will be present only in the approximation. The detailed coefficient consists of the detailed component of your signal. Right? For example, I say the music beats or some other even a noise. Suppose whatever I'm speaking in front of you, if someone wants to record it, right? So there is some disturbance. Maybe you are hearing my children are playing there, so they are creating some kind of disturbance. So really, I'm getting a disturbance from my children. So I just So what I'm trying to say, the speech signal, it's noisy, right? You want to remove the noise. A simple way to remove the noise without designing anything. If you do a decomposition of my speech signal, all my informations will be present in the approximation coefficients, and the noise, the fan impulse or the room impulse will be get added into the detailed component. Okay? So that is what about how the discrete Wavelet transform works. Next, as I told you, the filter. So what basically it will do, it is two sections. One is filter section, another one is sampling. We call it as subsampling. So there are two types of sampling we are doing, interpolation and decimation, right? So this one we call it as a decimation, decimation by 2, decimation by 4. It depends upon your application. Here it is decimated by 2 in this particular case. So in your analysis, my signal suppose consists of 100,000 data, right? So now if I go with a high pass filter and decimate it, then it changes to 500 components. And if you go with the low pass filter and decimate, I'll get another 500 components here. So the 1000 will be divided into 500 and 500. Now, these 500 will consist of some showing noise or detailed component. My original information is only this 500 component. So what further, I feel further noise is present here in the signal. So once again we go for the decomposition, but we are not going with the high pass filter, we are going only with the low frequency component. That is, this is a detailed component and this is a approximation component. So I take the approximation signal. Once again, I go for your decimation, downsampling, and low pass filter downsampling. The 500 is divided into 250 and 250. So this is what the multi-decomposition technique. So until you feel, my information is getting lost, I can go for the decomposition. There is also there is a different formula for that to find up to which level you can go for the decomposition. At the end of this, I published one paper in applied acoustics. So we use there. We use as a formula. We are finding the energies of the signal, and then after decomposition, so if the energy level is below some certain threshold, then we have to stop the decomposition technique. What is synthesis? So you use here decimation. Now you have to use the interpolation. It's called the interpolation. That is interpolation by 2. If you do here, you have to do by 2 here. Then once again high pass filter, then low pass filter, then interpolation, you will get the 500 component. Once again you will do the reverse process, is called synthesis of the equation. So basically how it will be is an approximation. Suppose we have a data x and y, the approximation will be, that is a low pass filter, and the output of the low pass filter, output of the high pass filter. So we have to do averaging and smoothing, that is x plus y by 2 for the low pass filter case. For the detailed component, y minus x by 2, high pass filter. So this is how it's used, approximation coefficient and detailed coefficient. So these are some of the results. If what I did in the my speech, noisy speech, I recorded my own speech here, and I added some noise here. So you can see that noise present here in the signal S. Now I use this is my original signal and a low frequency component A1. So this is my original speech, and a high frequency component, it is the detailed speech. You see the information from the S is simply followed the same pattern, whereas it is completely a noisy, right? So in image processing, we have 3 steps. It's a speech processing example so I given. It's an image processing, a decompose of a signal in the image, decompose of the image signal into a wavelet domain is complete a different scenario. To alter the wavelet coefficients according to the application, such as denoising, compression, edge enhancement, etc. Reconstruct the image with the altered wavelet coefficients. This is what the process in case of image. So basically, a resolution of the signal, which is measure of the amount of detailed information in a signal, is changed by filtering operation, and scale is changed by upsampling and downsampling operation. Just now I told about the previous diagram, right? So in this diagram, the upsampling and downsampling, that's what they mention about multi-resolution analysis. So whatever I told, I talked already, the same thing. So here DWT analysis at different frequency band with different resolutions by decomposing the signal into approximation and detail. The important thing is the resolutions will change. So DWT employ two sets of functions called scaling function and a wavelet function, which are associated with low pass and high pass filter respectively. So this is how in case of the image, I told the example for a speech, how it happens to the image, right? In an input image, which have rows and columns, then rows you have high pass filter, low pass filter. So here, in this case of approximation and detail, I will go with both the columns for once again the next level of approximation. Once again, high pass filter, low pass filter, then decomposition. Once again, both the approximation coefficient and detailed coefficients will be gone for the decomposition here, right? In previous case of speech signal, it has not happened because the speech signal consists of the detailed component will not give the information, whereas in an image, certain minute edges will be missed if you miss the detailed component. That's what it is, very important. You can see we have a input if you decompose, it has a 4-stage LL band and LH band and then HL band and HH. So you get LL is a low frequency information, low frequency with high pass filter, high frequency with low pass filter and high frequency band. So further if you go for the second stage, now almost the information will be present in LL. So LL is once again divided into 4 and once again it is decomposed. Now this LL, triple L will consist of maximum information. So once again it is decomposed. This is a multi-level in case of two-dimensional case. The same thing which I explained here. So you see the image, it's a linear image, original image. The first level decomposition, if you do, then you can see these are the detailed components and this is the information present, right? Then once again the second level of decomposition, you can see the image is getting lost here, right? The sort of image is blurred here, right? So the first level itself will give you a good thing, and noise also removed from this. So it's another example. Like so further it goes on, then it is a problem. Like you can lose your, there is a possibility of losing your original information. So the synthesis part, as I told, interpolation, and then a high pass filter and low pass filter, the reverse process. So there are certain applications which we are going to discuss. Data and image compression. So mainly it is used in data and image compression. These transforms are used. So image compression, you know, actually you want to compress the image. Data pre-processing. That's what I told about the leak detection. It's one such an example what I did in my postdoc. And you have so many things, even like when I do my field of interest is speech and the acoustic echo cancellation. You know about the acoustic echo cancellation. There will be a echo will be generated. That echo nature is not a additive nature, it's a convolutive nature. That means echo is simply the other person or myself, I hear my own voice after few delay, right? When I hear my own voice, right, I not only hear my own voice, along with that there will be some room impulse will be get added. It is not added, it is get convoluted. So it's very difficult to remove the convoluted noise. So if it is an additive noise, then we can easily remove the additive noise. But convoluted noise is very much difficult to remove it. So that is what I feel I used initially a pre-processing. So what I used is initially a wavelet pre-processing technique. I use DWT and then I use whatever they found, it's very suitable for me. So I'm not designing any new wavelet, and then I use the DWT pre-processing for level 3. Up to level 3, I can able to reconstruct the signal very good back. So what here, that particular nature of convolutive noise are somewhat okay with wavelet transform. After wavelet transform, 100% it is not removing. Some like 25 to 30% are removed. So then I decided, so wavelet transform is working well. Okay, then further what is the advancement? Then I used for eigenvalue decomposition. It works better than wavelet transform. Then I used the polynomial eigenvalue decomposition, which is PEVD, which works better than a wavelet. So like that, initially, if you want to do something, what are the existing methods, and based on the existing method, our innovation will begin. Because directly we cannot go and do something innovation of it. Because some standard papers and journals and scientists have proved that will be used for a very good pre-processing. So we have to start our research with the help of what is already existing, and then you have to go for the advancement. Then only you will understand up to which level the wavelet is working, what level is your desire, and how you are going to modify it, right? So then only the new innovation, a new kind of decomposition, or new kind of pre-processing you can able to get. So and it is used for the pattern recognition, that is a speech to text as well as text to word, and then so many pattern recognitions are there. Texture analysis, noise reductions. So this is what I'm talking about in my echo cancellation problem. You want to image resizing, image retrieval, object tracking. So these are some of the applications what available. So this is one speech processing example. So this is a noisy speech. After decomposition and getting, this is approximation value. So different levels. I go 3. This is a A3. I told level 3, and then these are the detailed component. Even the first detailed component is noise. All these 3s are completely noise, right? So see the original A3 is consist of the information. So these are the example with the modulation. I took a after modulation. See, we do a simple experiment in a lab like amplitude modulation. The output of the amplitude modulation look like this. This is output of the amplitude modulation. While we retrieving back, we are not simply using a sine wave. We also use a random noise to add in it. So what we'll do, the noise will be look like this, and denoise the signal will be like this. This is happened only with the help of the wavelet. You can see there is some there is some irregularities will be there, missing of data will be there, but that will be taken care separately. But it works well. So even this is the loss of information. What I feel, this is a modulated signal. These are completely noise. These are completely noise. These two some of modulation. So you'll be very careful while designing, while do the demodulations, while using a wavelet transform. The loss of information should be avoided. So these are some of the examples of what we done it in the lab. Both image, it's a noisy image, and this is using wavelet decomposition, the noises removed. And this one we add a additive Gaussian noise. And wavelet application in denoising. And this is the operation of how JPEG 2000 works, right? So you can get it in the net in this one, it's available. And a multiple level of decompositions of an image will take care. So it's an image fusion application, you can find it in MATLAB. So this is a mask, and this is a original image, you want to do the masking. So it is possible with the help of image fusion, is possible with the help of wavelet transform.
Sir,
See, we have, yeah.
Excuse me, sir. We are left with 10 minutes, sir.
How much?
10 minutes, sir. It's 11:50 now.
Yeah. I'm going to complete. This is my last slide.
Okay.
So, and this is image, Catherine image. The image is deep blur, and other side is deep blur. Then this kind of problem, you can take this portion with the help of wavelet, this portion, and fuse together, you get this clarity of image. It's possible. So these are many applications are there. So I'm pleasure to answer all your questions. You have any questions? That's in my presentation. So actually, I plan to give more the qualitative, like different application perspective. So still, I'm having a class by 12:15 now, so I'm limiting this.
So, dear participants, be free to ask questions to sir. Unmute yourself and ask the questions. Dear participants.
So I can take it in any questions?
Participants,
If no more question, then I can take it in two way. Nothing understands. If you not ask any question, that means you are not understand anything. In one way, the other way, if you clearly understand, you don't have any doubt, means you are 100% you have a satisfaction. So I'll take it in a second way as a positive thing.
sir, already participants in the chat box, they have given the feedback, sir.
Okay,
Like
okay.
this.
Chat box, yeah. Okay.
Okay. So, shall we end the session, sir?
Yeah. I thank Dr. Epsiba to give the opportunity for me. I'd like to give some more thing. I'm doing my research further in a machine and deep learning. In future, if it is possible, I try to give the exposure. Thank you.
Okay. Good afternoon, all participants, sir, Prasad, sir. On behalf of our Department of ECE, Pallavi Engineering College, I take this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this webinar on wavelets and its applications organized by our institute. At the outset, I thank our resource person, Dr. Mohana Prasad. We are really enlightened with your knowledge and presence, sir. We are thankful to our Honorable Vice Chairman and respected Vice Principal for their motivation and enthusiastic support. A special thanks to Epsiba ma'am, our HOD ma'am, and all the staff members for their support and coordination. And our heartfelt thanks to the active participants. Thank you, sir, for giving the wonderful speech. Thank you very much, sir.
Thank you, ma'am.
Okay. So we'll be ending the session now. Participant, please fill the feedback form. The certificate will be automatically sent to your mails once you fill the feedback form. Thank you. Thank you all.
Thank you, ma'am. Thank you, Prasad.
Yeah, thank you.
Ma'am, shall I close the session, ma'am?
ఏడున్నానే